Welcome everyone. In this video, I am going to talk about the very important Dijkstra's algorithm to find the shortest path between any two vertices in a graph. I will also be discussing about counting the number of paths between any two vertices in a graph of any given length. So that part I will be discussing later. So let's start. The first problem that I have taken here, we have to find the shortest path from the vertex A to the vertex Z. This kind of graph is known as weighted graph because we have associated a weight with each of the edges of the graph. This weight may be anything, like here this may be distance, cost, time. So depending upon the nature of the problem, the weight may have a different context. Now what are the steps involved in this algorithm? So the first thing that we do is that we assign a label to each of the vertices, and since I am starting at the vertex A, then I will assign the label 0 to the vertex A, right? And all other vertices will be assigned the label infinity, right? So initially we consider that every vertex is at infinite length. Now what we do, and in the next step, that since we are starting at A, we are going to block the vertex A, right? Because blocking means that we are not going back to this vertex. So since I am starting, there is no point going back to it because we are starting at A, right? Now what is the first step? That the distance of A to C, because I am going to look at all the vertices which are adjacent to A. So there are two vertices which are adjacent to A, that is B and C. So I am going to relabel the vertices B and C. So, and relabeling should be done only when we get a smaller label than the already assigned label to that vertex. So here the vertex has been assigned infinity, so any label will be certainly a smaller. So let us relabel it. So the distance from A to C is 2. So what I am going to do, I am going to cross this, and I am going to write 2, and in the bracket I will write A. This signifies that we have arrived at C from A, okay? And this distance is 4, so I am going to cross it, and I am going to write here 4A, just to signify that I have arrived to the vertex B from A, and the distance I have covered is 4. Now out of all the labels that are present in the graph, to all the vertices which are not blocked, because the vertex A is already blocked, so it means we are going to look at this label, that is 4, 2, infinity, infinity and infinity. So out of all these label, which one is a smaller? So certainly the 2 value is the smallest. So I am going to block this vertex C because this is the smallest label that has been assigned to the vertex C. Now we will repeat the process. When I say we will repeat the process, means that now I am going to look at all those vertices which are adjacent to C. So the vertices which are adjacent to C are A, which is already blocked, B, D and E. So I am going to relabel them. So how the relabeling should be done? This distance is 2, and if I move from C to E, we will cover this distance 2 plus this distance 10, so 12. So this vertex should be assigned the label 12, and here I will write 12, and in the bracket I will write A comma C, just to signify that I have arrived at E from A and then to C, and then I move to E. Okay. Now what label should I assign to the vertex D? Because this distance is 2, this distance is 8, so we cross it and we write 10, and not 10, yeah, so 2 plus 8 is 10, correct, 10, and in the bracket I write A comma C. Okay. Now I move to this direction and C to B, and when I go from C to B, we note that this distance is 2, which is already assigned, and then from C to B the distance is 1, so 2 plus 1 is 3, and 3 is less than 4. this is a very important observation. If we get a value greater than already assigned label, we do not change it. But if we get a smaller value, then we change it. So what we have to do, we have to change the label, and now it will become 3 and A comma C. Now two vertices are already blocked. Out of those which are not blocked, like B, D, E and Z, we can clearly see that 3 is the smallest value. So we are going to now block the vertex B, and the process will be now again repeated with the vertex B. So from B to D, if I move, the distance will be what? This is the distance 3, which is already assigned. So 3 plus 5 will be 8, and 8 is less than 10. So we can relabel it, and here I will write 8 A comma C comma B. And I hope you are getting why we are writing this thing in the bracket, because I have arrived C by when we started at A, then moved to C, and then to B, and then finally we arrived at D. Okay, so this distance is 8A comma C comma B. Now B is adjacent to D, C and A, but C and A are already blocked vertices, so I don't have to think about relabeling any other one, because just one vertex which was not blocked, I already have relabeled them. Now this is 8, this is 12, this is infinity, right? So clearly the 8 value is the smallest. So in the next stage, what we are going to do, we are going to block the vertex D. And once I block the vertex D, I am going to assign different label which are adjacent to D. So if I look at the vertices which are adjacent to D, those vertices are E and Z. C and B are also adjacent to D, but they are already blocked, so I am not looking at them. I'm just looking at those which are not blocked. So D to E is how much? 8, and then this 2 will become 10, and the already assigned label is 12. So 10 is less than 12, so I'm going to cross it, and I'm going to write 10 A comma C comma B comma D. And if I look at this, here it is 8, and then this distance is 6, so 8 plus 6 is 14. So I cross it and assign a new label, that is 14 A comma C comma B comma D. Okay. Now out of the unblocked vertices, there are two vertices which are still unblocked, that is E and Z. And a smaller one is E because its weight is 10 now. So I am going to block the vertex E. Okay. Now look at all those vertices which are adjacent to E. So the vertex which are adjacent to E is Z. So if I measure the distance, 10 is already the label that is assigned to E, and then 10 plus 3 is 13, and 13 is less than 14. So what we have to do, we have to cross this label, and we have to assign the label that is 13 A comma C comma B comma D, and then E, right? Now all other vertices are blocked. We already means we are arriving finally at Z, and there is no other possibility. So now I'm going to block Z as well. So what we have got in the end, is the shortest path, right? So what is the shortest path? Shortest path is, we started from A, went to C, then to B, then to D, and then to E, and finally we arrived at Z. If I put the arrows on the edges here, that will be easier for us to understand. So we moved from A to C, then C to B, then B to D, then D to E, and then E to Z. So this is the shortest path. And what is the shortest distance? So shortest distance in this case is equal to 13, because that is what we have got in the end. So in this process you are getting two things. You are getting what is the shortest distance and what is the shortest path, because the labeling, the way we are doing the labeling, we are also taking care. that how we are arriving at that vertex, and in the process we are also writing the vertices which we have come across. So we are simultaneously getting both the shortest distance as well as the shortest path. I hope this problem is clear to you. I am going to take one more problem so that you become absolutely clear about the concept. Okay. Now look at this problem, and here also we have to find the shortest distance from a vertex A to the vertex Z. So let us start without any delay. So what is the first stage? We assign the label 0 to A, and all other vertices are assigned the label infinity, right? So this is a very obvious step. And then we are starting with A, so I'm going to look at all those vertices which are adjacent to A. So A is adjacent to B and C. So let us relabel it cross infinity, and then write it is 3 in bracket A, right here 4 and in bracket A, right? Now since I started with A, I could have blocked A in the beginning itself. Now out of all those labels that are assigned to different vertices, clearly this vertex C has been assigned the least value, the smallest value. So we are going to block the vertex C, right? Because C is the least label. C has been assigned the least value. Okay, because this is a greedy algorithm, and at every stage we are looking for the smallest value that has been assigned to the label. Now we have blocked A and C. Now I am going to look at all those vertices which are adjacent to C. So E is adjacent to C, so let us relabel it, and when I relabel, it is 3 plus 6, that is 9. In the bracket I will get 1 comma C. It is 3 plus 3 is 6, so I will cross it and I will write 6, and in the bracket I will write A comma C. So this vertex labeled, this vertex labeled, this is also adjacent. Now look at this carefully. The B vertex is adjacent to C, but if I go from A to C and C to B, the distance will be 3 plus 2 5, because we have got 3 here, and if I take this path I will get 3 plus 2 5, which is more than 4, right? So that 5 will be more than 4, so in that case we are not going to relabel the vertex. I repeat it, whenever in the process of relabeling you get a bigger label, then you do not relabel the vertex. Now out of all the labels that have been assigned to different vertices, you can see that it is 4, 6, 9, infinity, infinity and infinity. So clearly the 4 is the smallest label, so I am going to block the vertex B now. Okay. Now repeating the process, you can see that B has 3 adjacent vertices, that is A, C and D, and A and C are already blocked. And if I look at C, this distance here is 4, and 4 plus 5 is 9. So 9 is greater than 6. So should we label it? No, it should not be labeled, because 9 is greater than 6. It means what? That we should not label it. So at this stage no relabeling has been done, and we just again compare the weights or the labels that have been assigned to different vertices. So we note that it is 6, 9 and all other are infinity. So we need to block the vertex D. You notice that it is also possible that in some of the steps the labeling may not be required, right? Because by relabeling we may get a bigger value which is not required. Now once we have arrived at D, we are going to repeat the process, and the process is that I am going to look at all the vertices which are adjacent to D. So the vertex which are adjacent to D are E, right, and F. So 2 more are adjacent here, remaining like C and B are already blocked. So I am going to look at E and F. So what will be the label that we need to assign now? So D to F is the distance 5. So this is 6. So I have to label it, and 6 plus 5 will become 11. So I will write 11 A comma C comma D. And if I move from D to E, the already assigned label is 9, but if I move from D to E, it is 6 plus 1 7, which is less than 9. So I'm going to cross it and I'm going to write 7 A comma C comma D, right? I hope you got it. So we have arrived at F, we have arrived at E. Now, ladies and gentlemen, out of all the labels, we note that 7 is the smallest because it is 7 here, it is 11 here, and remaining 2 are still to be labeled because earlier assigned labeled are infinite. So since E is the smallest, I am going to block the vertex E. Now, repeating the process, E to G, the distance is 5, so the label now assigned to G will be 7 plus 5, that is equal to 12, and here we will write A comma C comma D comma E, and E is not adjacent to any of the unlabeled vertices. D and C are already by unlabeled I mean unblocked. That is a mistake I made. So here E, I repeat, E is adjacent to G, which I already labeled, but I can't move from E to C because C is already blocked, and this will be kind of backward movement. So E to D also I can't move. Now, out of all those vertices which are unblocked, we see that the smallest weight is assigned to F. So next we are going to block the vertex F. Now from F we have two possibility. One, we can move to G, and another we can move to in Z. So if I move from F to G, the distance will be 11 plus 2, that is 13. But we already have a smaller weight, that is 12, so we are not going to do anything to this. And if I move from F to Z, it will be getting 11 plus 7, that is 18. So let us relabel it and write it 18 A comma C comma D comma F, right? What happens now? We have two vertices, and one is G and another is Z, and we look at the smaller one. So the smaller one is 12, so G should be blocked, so I blocked G again. Now once we blocked G, if I move from G to Z, the distance that I will have to cover is 4, and till G we have got the 12, so 12 plus 4 is 16. But the earlier assigned label is 18. 16 is less than 18, so I am going to cross it and I am going to write 16, and here I will write A comma C comma D comma E comma G, right? So means we have arrived at Z through this path. So now you know that I have blocked all the vertices. We arrived at Z, and we have got the minimum distance, that is 16, so I am blocking Z now. So what is the minimum or shortest path here? So the shortest path is equal to 16, and what is the shortest distance? Shortest distance is 16. I mean, let me change it. Shortest path is A to C, C to D, D to E, E to G, and G to Z. Okay, and shortest distance is equal to 16. I hope you are clear about this thing, that by distance I mean that what is the total length that I have covered, and by path we mean that through which direction we have arrived from A to Z. So this is, I think, clear to you. We have taken two problems. I would suggest you to solve some more problem at your end so that you become confident about the process, and in case if you come across any difficulty, you should let me know through the comment section. Okay, so now let us move to the next idea. So the next thing that we are going to talk about is how to count the paths between two vertices. So first of all, to understand this process, I will take example, but let us look at the expectation from us. So let G be a graph with adjacency matrix A. So the first requirement is that you need to write the adjacency matrix of the graph with respect to the ordering V1, V2, Vn of the vertices of the graph. The number of different paths of length R. So we may be asked to find the path of a specific length, length r from the vertex vi to vj, where r is a positive integer, equals ijth entry of a to the power r. Did you get it? If you didn't, let us look at this problem. How many paths of length 4 are there from a to d? Right? This is the question. So as I told you, that first thing that I need to do is to write the adjacency matrix corresponding to this graph. And when we are writing the adjacency matrix, we need to order the vertices. Okay, so let us write them in this order. The first is A, then B, then C, and then D. And we know that whatever the order we write here A, B, C, D. And A is joined to B and C, so there will be 1, A to B and A to C, and there will be 0 here. There is no edge between A to A and A to D. Now if I go to B, it is joined to A and D, so it is joined to A and D, which is not joined to B and C. For C, it is joined to A and D, so C is joined to A and D, not joined to the vertex B and vertex C. And if I talk about D, it is joined to B and C, so D is joined to B and C, not joined to A and D. So this is the first step to find the path of any given length, and here they are asking me to find the path of length 4. That is what we have to find. So what we did, we just first wrote the adjacency matrix. And one thing is clear, that the way we have labeled the vertices, so if I have to find the path of length 4 from A to D, so A to D is what position? A to D is the 1/4 position. Okay, because A is coming in the first row and D is coming in the last row, so A is the 1/4 position, right? Because in the previous slide I highlighted this. Let us look at the definition. It is saying that if you have to find the path of length r from vi to vj, where r is any positive integer, that equal to ijth entry of a to the power r, right? So if I have to find the path of length 4 from a to d, we have to first find what? We have to first find a to the power 4. Now to find a to the power 4, and if you are here at this point of the video, I am going to make you learn a very important thing, and this is going to be very interesting, so be till the very end. So what I am trying to say here is that some of you might be thinking that finding a to the power 4 is a difficult task, right? Because we have a 4 cross 4 matrix. But the process that I will explain to you, and this is not only going to help you in solving this kind of problem, this is a very general kind of linear algebra problem, and let us understand that. So suppose first I have to find a square. So to find a square, I have to multiply these two matrices, a into a. So I write it again for your convenience, because you are learning this thing for the very first time. So you should be clear about the process, and that is why let me put the effort. So I am writing a both a into a, so that is 0 1 1 0 1 0 0 1 1 0 0 1 and 0 1 1 0. Now ladies and gentlemen, there is a process known as column wise matrix multiplication. Okay, so what is column wise matrix multiplication? See, these two are 4 cross 4 matrices, and if I multiply them, what I will get? I will get a 4 cross 4 matrix, right? So to multiply this matrix, we are not going to take a row and column. We are going to multiply it column wise. If you are clear about row and column wise multiplication, then you can do that way also. But I believe that by knowing this method, you will find it more easier. So if you look at this column here, this column has 4 entries, 0, 1, 1 and 0. And these 4 entries are going to act as 4 scalars. So when I multiply this whole matrix by this column, I will get the first column of the product matrix. To get the second column of the product matrix, I will take this column, second column of this matrix, the post factor, the second matrix, and I will multiply it into this matrix. Similarly, to get the third column here, I will take the third column here and I will multiply the whole matrix, and fourth column will give me the fourth column of this. Now you might be thinking what I am saying. So just let us go back to your linear algebra class, and for the time being consider these columns as different vector: v1 vector, v2 vector, v3 vector, v4 vector. Don't confuse it with vertices because currently we are talking about graph theory, so some of you may confuse it with the vertices. No, I am calling this vector as v1 vector, which has 0, 1, 1, 0 as the entries. I hope you remember that anything like this 1, 0, 0 or something like 0, 2, 3, these are known as column vectors. So I am considering this as a vector here. The first column will be given by taking the combination of these 4 vectors. So how do you write the combination? You write the combination C1 scalar times the first vector plus C2 times the second vector plus C3 times the third vector plus C4 times the fourth vector, right? Now you might be thinking that from where this C1, C2 and C3, C4 will come. So these 4 numbers here will act as the scalars, like C1 is 0, C2 is 1, C3 is 1 and C4 is 0. So if I take the linear combination, I have to take 0 times this vector, right? So if I take 0 times this vector, I will get all 0 vector, 0, 0, 0, 0 plus 1 time the second the second vector here. So what I will get? I will get 1, 0, 0, 1. Then plus 1 time the third vector. So again I will get 1, 0, 0, 1. And 0 times, because this is the fourth scalar here, so 0 times the fourth vector. So 0 multiplied into anything will give me 0. So this is what we are getting. I don't have much space here, so I am trying to squeeze the things in between. Let me change the color so that you don't get confused. So basically what we got that this color is not changed. Okay, try it again. So what we got here is that the sum of these 4 vectors. So if you take the sum 0 plus 1 plus 1 plus 0, so basically you will get 2 and then 0 and then again you will get 0 and in the end you will get 2. So did you realize that how did I multiplied this matrix by this column vector? See, I am taking time because this is a new thing. Otherwise, if you are comfortable with the regular process, you can do that way also. But this is, I think, is an easier one. Now, can anyone answer that how to write the second column? In case if you think you can answer, pause the video and first answer and then continue watching. So here I will take 1 time this, means this vector, plus 0 time the second vector, plus 0 time the third vector, plus 1 time the fourth vector. So basically what we are doing, we are taking 1 time this and 1 time this, means 1 time the first column, 1 time the last column, and 0 time the second column and 0 time the third column. So if you combine all of them basically you will be adding the first and last column. So you'll be getting 0, 2, 2 and 0. Okay. So what will be the third column now? We already have got the first 2 column. To get the third column, we have to look at the third column here and combine these columns. So here we can clearly see that second and third column are same. So whatever we have got in the second column, I will get the same thing in the third column as well. but still I am repeating it so that you are clear about this. So here we take 1 time the first column and 1 time the last column, and 0 time the second column and 0 time the third column. So basically the scalars I am taking, this is the first scalar, this is the second scalar, this is the third scalar, and this is the fourth scalar. So I am in the end getting 0, 2, 2, 0. And to get the fourth column, what we have to do, we have to take 0 time the first column, 1 time the second column, 1 time the third column, and 0 time the last column. So the first and last column become 0, and we just have to add the second and third column. So I'll be getting 1 plus 1, that is 2, then 0, then 0, and then 2. So this is our a square. This is our a square. I hope it is clear to you. So since we have to find a to the power 4, we have to multiply a square into a square, and this is our a square and this is again our a square. So now what is the process? So the process is that I will be taking the first column here and I will be multiplying the whole matrix. So now look at this carefully, and let me change the color also so that you are clear about this. So what we need to do, we need to take 2 times the first column here, 0 times the second column here, 0 times the third column here, and 2 times the fourth column here. So 0 times the second column will make everything 0. 0 times the third column will make everything 0. So 2 times the first column will make it 4, 0, 0, 4. Let me write here that 2 times, if I multiply this by 2, it will become 4, 0, 0, 4. And the other 2 columns will be 0, 0, 0, 0, and then again 0, 0, 0, 0, and the last will be again 2 multiplied into this. So 4, 0, 0, 4. So I write 4, 4, 0, 0, 4. I hope you got this. So if I add them, what I will get? I will get 8, 0, 0, 8. What about the second column? 0 times the first, 0 times the last, 2 times the second, 2 times the third. So 4, 4, 0, 0, 0, 4, 4, 0. So I will get 0, 8, 8, 0. Third stage or third column, 0 times the first, 2 times the second, 2 times the third, and 0 times the fourth. So again the same thing, there is no change because these 2 columns are same. So I can write 0, 8, 8, 0, and you can see the first and last are same, so I can just write 8, 0, 0, 8. So this is what we have got a to the power 4. See, I have taken time so that you understand it properly, and this is a very effective approach. The row and column wise approach that you already know may be very time consuming, especially if the matrix size is bigger. And here, since we are talking about adjacency matrix, there will be a lot of zeros which will make our computation easier. So now this is the first stage. We wanted to find the path of length 4. So we have got a to the power 4, right? Now go back to the main point. What they have told you, that when you have to find the path of length r, you have to find a to the power r. And in this problem you wanted to find the path of length 4, so that is why you are calculating a to the power 4. So once you have calculated a to the power 4, what is the next thing that you have to do? Next thing you have to do is to find the ijth entry of a to the power r. Now this is important to note here, that what is the ijth entry. So we are finding the path from a to d, and a is our first vertex and d is our fourth vertex. So what is the entry that we are going to find? We are going to find ijth, that is in place of I1, in place of j4. So we are going to find 1/4 entry of a to the power 4, and 1/4 entry of a to the power 4 is what? 1/4 entry of a to the power 4 is that first row. Let me write it, 1/4 entry, 1/4 entry. So first row and fourth column. So this is the entry that we have got, 8. So the total path, total number of paths of length 4 is equal to 8. Okay, now we have got that idea that total number of paths are 8. So next let us find that what are those 8 paths, and I'm going to look at the graph here and going to decide. I'm removing this part because this is something that I wrote to just explain you. So ladies and gentlemen, let us count all those paths and see, this process only gives you the total number. What are those paths that you have to look at the graph and decide. So I'm going to write all those 8 paths for your convenience. So, and you need to be focused on the screen to understand it. So suppose I move from A to B, and then B to A back, so A back, and then A to B, and then to D. I repeat it, A to B 1 length, B to A 2 length, then A to B 3 length, and then B to D 4 length. I am saying path, I means I am not restricting you to not repeat the edges. I already have told you that we are using the notation in previous video. This was highlighted that by path we mean that the edges may be repeated. By simple path we mean that edges should not be repeated. So I moved from A to B, and when I move from one vertex to another vertex, means if I move across one edge once, then we are covering a path of length 1. So see, I moved from A to B, so 1 length, then B to A 2 length, and then again A to B 3 length, and then to D, so 4 length. So the first path is AB, ABD. Now what is the next path? The next path is A to B. I am writing here A to B length 1, then B to A length 2, and then A to C, so length 3, and then C to D, that is length 4. I repeat it, A to B, let me draw the arrow, A to B, then B to A, so 2, and then A to C 3, and then C to D 4. So this is another path of length 4. Rest of the path I am going to write it, you have to verify, so you can certainly verify. A, B, D, B, D. Then A, B, D, C, D. Another is A, C, A, B, D. Another is A, C, A, C, D. Then you have A, C, D, B, D. And finally you have A, C, D, C, D. See, I have written it. I would request you to verify that all of them are of length 4, right? So I hope you are clear about the process. I repeat the whole thing in just 30 seconds. That suppose there is a problem, and in that problem you have to find the path of length, suppose any number, means suppose I say length 7, right? So what is the first step? First step is to write the adjacency matrix for the given graph. Step number 1. Step number 2, find a to the power 7. Now you might be thinking finding a to the power 7 is a difficult task. Yes, it will certainly take some effort, but if you follow the process by multiplying it column wise, it will be easier. Once you have got a to the power 7, in third step you have to locate that. Suppose you want to find the path between second vertex and sixth vertex. Second vertex, and now how will you count the second vertex? The way you have ordered them, right? When I say ordering, like here I am ordering in A, B, C, D. So A is the first one, B is the second one, C is the third one, D is the last one. So similarly, the way you order them, so you look at the second vertex, means you go to the second row, and then you go to the sixth column. So which entry you look? You look the entry in the second row and sixth column of the matrix, means 2 6th entry. And if 2 6th entry, suppose it say n, so it means what? That the total number of path from the second vertex to sixth vertex of length 7 is equal to n. Now this process gives you this idea that total number of how many total number of paths are there. Next, if they are asking you to write the paths, then you have to look at the graph and since you are already aware that it is going to be this many number of paths, then you have to use your trial and error approach and to count all the possible paths the way we have counted all the 8 paths here, right? So in this video we talked about two very important things. One is Dijkstra's algorithm, very famous, and this Dijkstra's algorithm is a very important problem for most of the examination. And then this problem of finding the total number of paths between any two vertices. So I hope you have understood it. In case of any doubt, I would request you that put your doubts in the comment section. From my side, this is all for this video. I hope you enjoyed it. So in that case, you need to share this with your friends and press the like button also, so that keeps me motivated. Thanks for watching.